Welcome to further mathematics class. In this class, I will be taking you through mappings and functions. Under the lesson outline, we will be discussing mappings, functions, one-to-one mappings and onto mappings, special and composite mappings, and lastly, inverse functions. Now to define the terms. Given that x and y are non-empty sets, if there is an operation which associates every element x in x with a unique element y in y, such operation is called a mapping. The set x is called the domain, while the set y is called the codomain. The element y in y is called the image of x in x. A subset of y, which is a collection of the images of the element of x, is called the range, and it's denoted by f of x is equal to y. Or in any of the three cases, you say that f is a mapping from x into y. One-to-one mapping and onto mappings. Given that f is a mapping from x into y, f is one-to-one or injective mapping if every element in x is mapped to a unique element in y. In other words, no element in y is mapped to by two or more elements in x. F is onto or surjective mapping if every element of y is mapped to by some element in x. In other words, no element of y is left out. In this case, the codomain is equal to the range. F is bijective if it is both one-to-one and onto mapping. This means the combination of one-to-one and onto mapping is called bijective mapping. Functions. What is a function? A function is a mapping whose codomain is a set of real numbers. What are real numbers? Real numbers are positive and negative numbers. The numbers include integers, rational numbers, and irrational numbers. Consider the mapping below. 2 is mapped onto 5, 3 is mapped onto 7, 4 is mapped onto 9, and 6 is mapped onto 13. Both domain and codomain are set of numbers. The mapping f is a function. So from the diagram, we observe that 5 is the image of 2. And we say that f of 2 is equal to 5. Also, f of 3 is equal to 7. F of 4 is equal to 9. And f of 6 is equal to 13. Now, y in y is the image of x in x. And the general equation is f of x is equal to 2x plus 1. Meaning that y is a function of x. Let's consider this example. Example 1. Study the problem below and answer these questions. A. Find the domain D, codomain C, and the range R of the mapping. Find the rules of the mapping. C. Is the mapping one-to-one or onto mapping? Here is the question. The domain D are all the elements in X, which are -1, 2, 3, and 4. And the codomain are all the elements in Y, which are 7, 5, 3, 0, and -3. Range is a subset of the codomain. That is, all the elements of the codomain that are images in the domain. If you observe from the diagram, 0 is not an image in the domain, and that is the reason why the range is -3, 3, 5, and 7. Now the second question, find the rules of the mapping. Now from the diagram, the rule of the mapping, f of x is a linear function. And why can we say it's a linear function? It's because there is no element in the codomain that is an image of two elements in the domain. Then we try linear function f of x is equal to x plus 1. So if you try x plus 1, when x is equal to -1, therefore -1 plus 1 is equal to 0. Now from the diagram, -1 is mapped onto -3. So the image of x, which is y, supposed to give us -3. And since it is 0, it means the equation is not valid, it's not correct. Even though other values of y are correct, the equation still remains incorrect. So let's try x minus 1. We change the signs. So when x is equal to -1, -1 minus 1 will give us -2. So -1 in the diagram is mapped onto -3. So -3 is supposed to be the image, and since our answer there is -2, is not correct. By changing the coefficient of x, we try 2x plus 1. So when x is equal to -1, 2x plus 1 will give us 2 into brackets -1 plus 1, and the answer will give us -1. So since -1 is not an image, it means it is also incorrect. Now let's try 2x minus 1. If we try 2x minus 1, when x is equal to -1, therefore 2x minus 1 is equal to 2 into brackets -1 minus 1, which is equal to -3, which is correct. So in the diagram, -1 is mapped onto -3. So this equation is actually correct. Now if you try to confirm, we'll see that what other values of x will give us the corresponding images in y, and that is the rule of that mapping. Now the last question, is the mapping one-to-one or onto mapping? Let's start from 7. 7 is the image of only one element in the domain, and that element is 4. Now 5 is the image of only one element in the domain, and that is what? 3. So 3 also is the image of only one element in the domain, which is also 2. And lastly, -3 is the image of only one element in the domain, and that is -1. So since every element of x is mapped to a unique element in y, therefore it is called one-to-one mapping. Now it is not onto mapping because the codomain in this case is not equal to the range. Special and composite mappings. Under special mappings, we have the identity mapping. Let Fi, that is a mapping from x to x, be a mapping defined by Fi of x is equal to x. For all x belong to x, then Fi is called an identity mapping. It is a mapping which takes an element onto itself. Fi is a mapping from x to x. From the diagram, x is mapped onto x, y is mapped onto y, and z is mapped onto z. And this kind of mapping is called an identity mapping. The second type of special mapping is called constant mapping. Let FC is a mapping from X into Y be a mapping which assigns every X belongs to X the same image K. Then FC is called a constant mapping if for every X in X, f of X is equal to K, where K is called constant. And from this diagram, FC is a mapping from X to Y. X is mapped onto constant K, Y is mapped onto constant K, and Z is also mapped onto constant K. So this kind of mapping is called constant mapping. Composite mapping. Let F, which is a mapping from X to Z, and G, which is a mapping from Z to F, be two mappings such that the codomain of F is the domain of G. The mapping F takes an element in X and produces an image in Z. The mapping G takes an element in Z and produces an image in Y. The mapping G of F takes an element in X and produces an image in Y via Z. Now this diagram perfectly explains that the mapping F takes an element in X and produces an image in Z, while the mapping G takes an element from Z and produces an image in Y. And that is the reason why it is called composite mapping. From the diagram, mapping F takes an element from domain X and produces an image in codomain Z. Also, mapping G takes an element from domain Z and produces an image in codomain Y. This means that the mapping of G and F takes an element in X and produces an image in Z, and that image is A, and also an image in Y, and that image is X. So that is the reason why G and F of P is equal to G of A, which is equal to X. And that is the same for the other result, and it is called composite mapping. Let's consider this example. Example 2. Let F, that is a mapping from X to Y, and G, that is a mapping from X to Z, be mappings on the set of real numbers defined by f of X is equal to X plus 1 and G of X is equal to Y plus 1 squared. Find G of F. It is established in the question that f of X is equal to X plus 1 and G of X is equal to Y plus 1 squared. So to solve for G of F is the same thing as GF of X. So in the solution, we substitute for f of X in GF of X, and that results to G of X plus 1. Recall that G of X is equal to Y plus 1 squared. Therefore, GF of X is equal to X plus 1 in brackets plus 1 all in brackets squared. Therefore, when we simplify that, we have X plus 2 all squared. And when we expand, we have S squared plus 4X plus 4. And that is the solution to that question. Inverse functions. Consider the function 2x plus 3 on the set A with the element minus 2, 1, 3 into set B with the elements minus 1, 5, 9. Illustrated in the diagram below. F is a mapping from A to B. Now, minus 2 is mapped onto 9. At the same time, minus 2 is mapped onto minus 1. And 3 is mapped onto 9. The function f takes an element from the set A to produce a unique image in the set B. Alternatively, the function f can be defined as the set -2, -1, 1, 5, and 3, 9. That is, function f is equal to -2, -1, 1, 5, and 3, 9. The relation G can be defined as the set of ordered pairs. G is equal to -1, -2, 5, 1, and 9, 3. And from the diagram, we see that G is a mapping from B into A. 9 is mapped onto -2, and at the same time 9 is mapped onto 3, while -1 is mapped onto -2. The relation G is a mapping, and it is called the inverse of the function f, and it is usually denoted by f raised power -1. That is the inverse of that function. Thank you for listening.